Well, it's an honor to be invited to the Dirac lectures. Unfortunately, I got into physics a bit too late to meet Dirac. I would have enjoyed that very much. So today I'm going to be talking about effective field theory, and I tried to think about what's a succinct definition of effective field theory. I'm going to be using EFT all over the place because it takes too long to write effective field theory. So I decided it was lying about short distance physics and getting away with it. So this actually goes to the heart of the way one thinks about quantum field theory in a modern sense. And in a way, it is in contrast with the way Dirac and his cohort thought about quantum field theory. In fact, Pierre Ramon told me a story about coming here to give a talk and chatting with Dirac afterwards and finding out that Dirac thought his life's work was a failure because of the infinities in QED. And that is not at all how we think about QED now. And the way effective field theory works is it's not just a technique for simplifying your view of the world or something, but it goes to the heart of renormalization because short distance physics is where all of your infinities are coming from. And the idea is pretty basic, which is that we don't know what exists at short distance physics. There's no reason to think that our theories above where the accelerators can reach have any reality to them. And in fact, the interesting thing is you can change your description of short distance physics and the long distance physics will still be the same. So a lot of the problems that Dirac saw in QED are probably fictitious because they have to do with this incorrect theory of the short distance physics. But effective field theory is a lot more than that. It's an extremely useful tool, and it becomes sort of a way of thinking that affects how one does physics in almost any field. And so you'll find that these techniques now are used in things as far away from quantum field theory as the classical inspiraling of black holes and the production of gravitational radiation, or the discussion of high energy collisions when particles are going very fast but are collinear. That's a different type of effective field theory. And so basically it's being used wherever there is a big hierarchy of scales, and it's an extremely powerful and pretty simple idea to apply. So there are sort of two different uses of effective field theory. One is the bottom-up approach. Okay, so you describe all possible short-distance physics in terms of contact interactions. So it gets reduced to contact interactions between light degrees of freedom. So you don't have to know what's going on at short distance. You replace everything with delta functions. The low energy particles get close together. I don't know what's going on there. I'll approximate that they're sitting on top of each other. Something happens and they bounce off, okay? So the reason why this is so powerful is because we know something about the light degrees of freedom. We know the symmetries that control the theory. And so we can write down a limited number of ways that they could interact at short distance. And each will come along with an unknown coefficient, how strong that interaction is. And then we can go and we can study experimentally and figure out what those constants are numerically, maybe they're zero, and then try to figure out what the short distance physics is based on that. And so the quintessential application of this is Fermi's theory of weak interactions. He was an unusual fellow in that he was a great theorist and a great experimentalist, and I don't think the world's seen anything like that since then. So he didn't let problems of infinities get in the way of trying to describe the physics he was actually seeing. And in particular, he was looking at the weak decay of the neutron into a proton and electron and wanted to understand that. We'll talk more about that. Another use of effective field theory pioneered by Weinberg mostly was to take the standard model, which is in particular the SU2 cross U1 part of it. Well, I should put the color there too. And look at possible extensions, not by trying to guess a theory of everything, which is another activity people do, but rather to look at all possible contact interactions arranged in a hierarchy of importance and use that to gain information about physics beyond the standard model. Normally abbreviated as that. Another application is what I'll call top-down, where you know this short-distance physics. And you want low-energy phenomenology, or say long-distance phenomenology. So in this case, what you do is you take the long-distance physics, which may be very complex, and you reduce it to a few contact interactions between the light degrees of freedom, which can greatly simplify your calculations. And examples of this, for example, are when you take the standard model and you want the low-energy flavor physics, which you're going to hear more about in this series. It turns out that the effect of the strong interactions on the flavor physics can look very complicated, but in an effective field theory way, it becomes very clear how to sum up the important stuff and ignore the less important stuff. So it's a very useful tool to make the problem tractable. This still involves perturbative QCD, but then another place where it's applied is non-perturbative QCD, namely down at very low energy where it's strong. This is a theory where we know the theory. This is a case where we know the theory. We can write down the Lagrangian in a very short little expression, but we don't know how to compute with it because it's nonlinear, it's got infrared divergences, it's very difficult. But the very low energy form of QCD is not that complicated. It involves mesons and nucleons. And so we can discuss the theory of mesons and nucleons, the low energy degrees of freedom, constrained by the symmetries of QCD, but otherwise replacing all of that complex stuff of gluons and quark-antiquark pairs with contact interactions. So that's another case where the top-down approach is very powerful. So why is this possible? There are some cases in physics where there is no separation of scales. I think the most famous one is turbulence, where the long-distance behavior depends on what's going on at short distance. And that makes it an extraordinarily hard problem to understand. But luckily, most aspects of quantum mechanics, you don't have to deal with that. So at a very basic level, what we're talking about is a Taylor expansion. We're going to go well beyond that, but let's consider I chose a hypothetical experiment which is very difficult to do experimentally. Namely, scattering of two neutrinos off each other. I choose this because it's simple. There are not many ways they can scatter. And in the standard model, the primary way they'll scatter is through a Z boson. And this has a mass of about 90 GeV. But I might be interested in neutrino scattering in astrophysical contexts where the energies are MeV. Well, if I look at the scattering amplitude, I'm going to get something that looks like G squared over S minus mz squared, where S equals the center of mass energy, frame energy, squared. So in other words, if I have E over 2 and P coming in, and on this one I have E over 2 and minus P, then this would just be E squared. And so what this tells you is that this is the propagator for the Z. When S is near mz, I get a big amplitude. That's because I've created a real Z that can wander around the universe for a long time before it decays into a neutrino-antineutrino pair. But at very low energy, so as S goes to 0, this is just minus G squared over mz squared. Or if I want a little bit more accuracy, I plus G squared over times S over mz to the fourth. And this is possible because if I look at this amplitude, sort of trivial here, in the complex plane, well, there's a pole here at mz squared, and I'll get it off the real axis typically, so it's a little bit below the real axis. But you know from complex analysis that I can then do a Taylor expansion around here with a radius of convergence of, I guess this is squared. As long as you're in this region here, you can do a Taylor expansion, no problem. And so this expansion is good. Now, what happens if I go to slightly higher order in quantum effects? Well, before I do that, what I want to do is mention some dimensional analysis. So particle physicists like to set h bar equals c equals 1. You can tell what sort of physics people do by what they set to 1. If you don't set, if you're doing non-relativistic physics, it's usually not convenient to set c to 1. If you're doing classical physics like soft condensed matter, polymer filtering, where quantum mechanics doesn't play a big role, you don't want to set h to 1. If you're a string theorist, you set everything in the world to 1 and claim you've solved everything. So when you do this, then you find that length and mass are related in dimension. So I'm going to talk about mass dimension. And I'm going to use this notation, which I don't know how widespread it is. I'm going to say that the dimension of M is 1. That is mass dimension 1. It comes in units of mass, or if you want energy. So I might say a particle has mass GeV. But so do a whole bunch of other things. Energy does, and momentum has the same, because mass times velocity, and velocity is set to 1, or it's in units of c. But also we know from de Broglie that p and 1 over x have the same dimension, so d by dx has a dimension 1. They all have mass dimension 1, while x and t have dimension minus 1, 1 over mass. And a cross-section, which is an area, therefore is minus 2. So if you want to study the cross-section for nu bar goes to nu bar, and you just take this leading term here, well, we know that this goes like the amplitude squared. So I'm going to approximate it with that leading term. Okay, oh, and I have to tell you that gauge couplings are dimensionless. So this goes like 1 over m to the 4th, but I just told you that the cross-section has to go like 1 over m squared. So something has to come in to give you another mass squared upstairs, and that'll come from the phase space integral when you add up your amplitude squared over all possible final states. And there's no dimension in the problem, really. The neutrino mass is so small, and I'm going to assume we're at energies well above the neutrino mass, that the only dimension is the energy you're doing the experiment at. So you're going to get a power of s out in front, which has dimensions mass squared because it goes like an energy squared. And this has important consequences. That means that this goes to 0 as s goes to 0. Sorry. That's sort of simple dimensional analysis, but it explains why this is such a weak interaction. And in fact, that's where we get the name weak interactions. Fermi's theory described an interaction which in itself, intrinsically, it's hard to say it's small because there's no small dimensionless number associated with it. Rather, he said, let's just use this as our starting point. And so the Fermi theory was that this goes like G Fermi psi bar psi squared, where this goes like G squared over, in this case, mw squared, which is about equal to G squared over mz squared. You're going to see a lot of squiggles in my talk. I'm not going to do numbers that are very accurate. I'm not interested in that. So he did something which is sort of interesting here. Over here I was talking about Taylor expanding an amplitude. But that's sort of stupid. Why would you want to calculate an amplitude in a complicated theory and then just Taylor expand it? That doesn't really gain you information. But the cool thing is that this expanded amplitude can be computed directly from a simpler theory. This is much simpler than the standard model. It just says that there are four fields which come together at a point. And of course, Fermi was not interested in neutrino scattering. He was interested in n goes to p E minus, and then they knew there was missing energy, which we know is an antineutrino, but of course they hadn't detected it then. So you put you turn this around and you say this is a neutron, and it turns into a proton and an electron and an antineutrino. And this is the tree-level application of his interaction, which is just basically G Fermi. And G Fermi, numerically, so it's this quantity here, which is about 10 to the minus 5 GeV to the minus 2. And so a GeV was more energy than was available to Fermi at the time, and there's a 10 to the minus 5. So this was, this decay, the energy exchange is about MeV. So when you put in the phase space factor, same thing as that happened here, to get the dimensions right, you find that down at an MeV, this is an incredibly slow interaction on the scale of particle physics. It's like, order 10 minutes. While if you ask how long does it take for a strong interaction particle to decay like the rho or the delta, it's 10 to the minus 24 seconds. So this is really weak. And it's very simply understood just by dimensional analysis. But it's important to note that this is not intrinsically a weak interaction in the sense that if I go to high energy on the order of mz, when s is on the order of mz squared, then the size is set by g. And g is not small. It's order like the QED coupling. Okay, well, what happens now if I start computing with loops in this theory? Radiative corrections. Two interesting things happen. So radiative corrections is just a statement that we're doing perturbation theory. We don't know how to solve these nonlinear theories exactly, except for in a few special cases in one dimension, one plus one dimensions. So we're doing perturbation expansion, and a loop expansion is equivalent to an expansion powers of h bar. So you're looking at more and more quantum-like effects as you go to higher loops. So let's look at one thing you might imagine is a Z and an internal loop of neutrinos. Now you find the amplitude has something built into it that is very different than the simple structure we saw over there. From this loop, you get something that looks like the log of 1 minus s over 4 m neutrino squared. This becomes imaginary when s gets bigger than 4 m neutrino squared, which is to say that if the energy coming in is enough to produce real neutrinos on shell, because that is the minimum energy this costs is twice the neutrino mass, so this is squaring twice the neutrino mass, then this becomes imaginary. And if this really was real scattering, then I know I have that much energy coming in because these were real neutrinos. So this looks terrible because now when I look at the analytic structure, here I have this pole at mz squared, but now I have a cut that goes all the way down to 4 m neutrino squared, which is incredibly low. It's less than an EV. M neutrino is less than an EV, maybe much less. So now it looks like, how in the world could this Taylor expansion ever work? You can't expand this for low s if s is bigger than m neutrino. But the nice thing is that in the Fermi theory, you have a graph where your neutrinos bounce off each other. Like that. And this loop has exactly the same log with the same coefficient. So in fact, you're not asked to Taylor expand this part of the amplitude. You get it for free in your effective field theory. So that's nice. So I dodged a bullet there. But what happens when I look at a muon neutrino in here? Still electron neutrinos out here, but I put in a muon neutrino here. This will also have a similar log, which will destroy the expansion. And there is no new, if there's no new mu in the Fermi theory, then I'm screwed, okay? I've tried to expand something, but there are all these non-analytic things getting in the way. So the moral is you must include nu mu in the effective field theory for energies greater than 2 m mu squared. Then I'll get that non-analytic part for free and I don't have to try to Taylor expand it. You can keep going with this. I could do, I can put an electron here. Suppose I want to look at energies bigger than half an MeV. I have to add the electron. And then if I go to another loop, I could put a photon here. That'll lead to more non-analytic behavior because I have enough energy to produce a real photon. Anything you can produce for real will cause all sorts of non-analytic stuff to appear in your amplitude. So I have to include the photon. And so on. What I have to include is all light degrees of freedom where light means m squared less than about the energy where you're working on. With an understanding that as s gets close to m squared, I'm going to start getting big corrections because I'm reaching the limit of my radius of convergence. So there's a couple cool things here, which is that If you include your light particles and you have your effective theory, and you find that as you go to higher energy, it starts behaving worse and worse, that is a sign that you're getting close to a new particle. So what would happen? Well, if S gets bigger, you have to start including this term here. Okay, and the way I'd include that in the Fermi theory is I'd have something that looks like psi bar psi d squared psi bar psi, because this would pull in the energy being carried by those neutrinos. And I'd have to have this divided by mz squared to reflect this extra power of mz there, with the G Fermi out in front, which does the other g squared over mz squared. So it's a higher dimension operator in the sense that this d squared has dimension 2, so I have to divide by a mass squared to put it in my Lagrangian. So let me go back to dimensional analysis. We know that S, which is the action, has the same dimensions as h bar, which is set to 1. So we know that the mass dimension of S is 0. It's dimensionless in our units. But it's also equal to the integral over space-time of your Lagrange density. And this goes like dimension minus d, and therefore this must have dimension d. So the Lagrange density has to have the dimension of the space-time you're working in. All fermions are described by the Dirac theory, which is psi bar I d slash minus m psi. This has the mass dimension 1. If we're in d equals 4, 3 plus 1 space-time dimensions, then the whole thing has dimension 4. And psi and psi bar have the same dimension, so that means that the dimension of psi is 3/2, because psi bar psi has the dimension 3. So if I look at this operator, I can say this has dimension 3 plus 3 plus 2, so that's 8. Our Lagrange density has to have dimension 4 if we're in 4 space-time dimensions, so there are 2 inverse powers of mass. One is hiding in G Fermi, and one's this explicit power here. So this extra d squared is what we call a higher dimension operator. Higher dimension operators go with higher powers of mz. So at low s, these are smaller and smaller effects, and I can ignore them. But if I start finding my theories breaking down, then I have to start including them, and that is telling you, oh, I must be getting close to something. There must be some new physics on the horizon that's starting to make my theory break down. Note that even though they knew the dimension of G Fermi, if G Fermi is given by G squared over mz squared or G squared over mw squared, you actually don't know what the W mass is because you don't know what G is. And when I was a student, undergrad student, I once saw a huge stack of phys rev letters that was being thrown out and was sitting in the hallway of the physics building, and I just started thumbing through them, and I found one which had the theoretical explanations for the discovery of the J psi, which had just happened. And there were 5 theoretical papers, one of which was completely right by Appelquist and co-authors, and 4 which were completely wrong. And one of them was by Schwinger, and Schwinger said, it's the W. You're seeing the resonance coming from this propagator. Because he thought that the effective theory had broken down, we were actually at an energy where it could produce the W. Yeah.
So theoretically, let's say, we expect the divergence, right? And then nothing, but if you open the box of the experimental data, the high energy, actually the data doesn't show anything. What do we do?
If the data what?
Data doesn't show any like.
So that's where we're at, right?
Yes, exactly.
We're right. Everybody thought you'd see new particles at LHC, but if you don't see new particles, not a problem, because maybe everybody was sure there'd be particles at 10 TeV or something. So we'd be able to see them through radiative corrections or through these little deviations from the standard model. And it's not correct to say there have been no deviations, because one thing that's been discovered, not at LHC, are neutrino masses. And neutrino masses don't occur in the standard model. And as I'll show you, they come from a higher dimension operator. But overall, the LHC accelerator physics has not found traces of this new physics. And it's what people who, in the early days of grand unified theories, called the desert. The desert was the absence of new particles between the standard model and the grand unified scale at 10 to the 16 GeV. You had a question?
Yeah. So when we're adding terms of our expansion, was there any, like, I guess, historical intuition as to, like, how many terms they were adding before they were like, there's something there?
So physicists are lazy. They like simple theories. If you have to start adding too many terms, you feel like you're like totally adding orbits on orbits, and it's not worth your time. You should start over with a new theory. And that is the effective field theory telling you that your old theory is breaking down. It's time to really start looking for a new one. So you typically do not take many terms.
Say anything beyond linear or...
So in this case, I don't know anybody going beyond the Fermi theory. I know in the strong interaction where you study meson interactions, people go to like third order or something like that. Okay, so what we've learned here is that really what an effective field theory in this case is, you're taking this interaction, and if you looked at it with a microscope, that you would see the W or the Z, and we're just shrinking this down. We're saying that our eyesight's not very good. It looks like a point to us, okay? Because we're probing with low energy. You can't resolve short distances with low energy. So this looks good, but it was regarded with horror by most quantum field theorists from the time. Because, yes, at tree level, it gave a nice phenomenological description of neutron decay, but so I just showed you that loops are fine if you included enough light degrees of freedom. I showed you what's called the IR behavior. Which is the singularities that occur at low S. And we got that right by including all of the light particles in the world. But there are UV problems with loops, the high energy part of the loop. If I look at this diagram here, I get a G Fermi squared, and I get an integral d4p, and then I have two propagators, two fermion propagators, which go like 1 over p squared, and this is a divergent integral. It diverges for large p, not p near where I'm doing my experiment, but virtual p that lives inside that loop. So if I have to put a cutoff on the theory, then it goes like lambda squared times G Fermi squared. It's infinite as I go to lambda goes to infinity. Lambda is not real. I shouldn't have to keep it finite. So the Dirac generation thought you had to have all your cutoffs go to infinity, or else the theory really didn't make sense. So this is called regularizing the integral, which is a fancy way of saying kick the integral until it's finite. So the next stage is, so this is regularization. And then there's renormalization. This short distance behavior remember I said that when you're at high momentum, everything looks like you're at very short distance. So we're talking about short distance behavior where this looks again like that. That looks a lot like the Fermi interaction. So you absorb into the Fermi interaction. So you say that G Fermi goes to G Fermi minus G Fermi squared lambda squared, so that you have a piece at tree level now which cancels the bad part there. And that what's left over is something finite that you can then measure in the lab. So this looks sort of revolting, but you actually see this in classical electromagnetism too. If you try to calculate the mass of the electron, including the energy in the electric field, it's divergent because the electric field goes to infinity fast near the electron. So you have to say, well, okay, I know I can move an electron. It doesn't take an infinite amount of energy to budget. So somehow this electromagnetic energy is canceling off some bare energy, which has to be negative to cancel it out. That's sort of weird, but okay. It's got to be an artifact of how we're calculating things. It can't be a property of nature. So we say we're doing something weird with this perturbative expansion, and we have to do tricks to make it work. But we can make it work. We can absorb this graph into G Fermi and continue our work. But there are other graphs in the problem. So if I look at this loop, now I have integral d4p times 1 over p to the fourth. That is still divergent. It goes like the log of lambda. And this was, therefore, it requires a counter term, an interaction that looks like that in the Lagrangian to absorb that infinity. Well, I hadn't wanted to put that in. I was never going to do the scattering of 4 neutrinos off 4 neutrinos. Or 4 neutrinos off each other. But this says I need to have that interaction in my theory if I want to make sense of my calculations. So I throw this in. I don't know how to measure the finite part though. So I don't know what to do with this, okay? And then you start sticking this in graphs, you generate more and more, and pretty soon you find that you need an infinite number of couplings in your theory to absorb all the infinities, and therefore you have to do an infinite number of experiments in order to fix their values. So renormalization fails. And you can see that the problem arises from the fact that I have a coupling constant here that goes like inverse dimension, because the more interactions I include, the more powers of inverse mass I put in, and the more powers I'll get of lambda upstairs to get the dimension right. And so high powers of a coupling like G Fermi will lead to high powers of lambda typically, or high powers of external fields. If I took one of these, an operator like this, and I tie these lines together, well, this came from psi bar psi cubed interaction, which is dimension 9, so we would have had to have something like G Fermi. Well, let me put an extra one. So this would be fourth, okay, which is dimension 12, so I'd have to have G Fermi to the fourth out in front to get the dimensions right. So now this looks like it's renormalizing our favorite interaction again, but now it's got a G Fermi to the fourth. So it's got to have a lambda to the 6 out in front of it in order to get the dimensions right, because this has to look like a correction to G Fermi. And you see that getting operators with many external fields is bad because it feeds back to the low dimension operators, and you get all sorts of divergences. So if I say my Lagrangian is a sum of operators times coefficients. So these are numbers, these are the coupling constants, and these are the operators. And if I say that the operator's dimension is d plus little m, let's say little n, then the dimension of C must equal minus n, because we know the Lagrangian has dimension d. And so we can sort of see that operators with n positive, 0, or negative are going to have different behaviors, where when the dimension of C is negative, we have problems with renormalization. So if we have operators with dimension greater than d, the old school discussion of this would say this is non-renormalizable. But the new school, which is largely due to Wilson, Ken Wilson, says this is sort of foolish. When you say non-renormalizable, you're looking at the short distance behavior, which we know nothing about. We've never done an experiment up where this thing is diverging. You've gone past the Planck scale, okay? We don't know anything about quantum gravity. Why are you saying that this is important? He said it's the low energy stuff that's important. We've seen that for high dimension operators like the Fermi interaction, which is dimension 6, it is unimportant at low energy. So he says focus on the low energy, and he calls this an irrelevant operator, which just means small. This means large in UV, and this means small in IR. And this is what's important. If you have an operator whose dimension is less than d, the old school picture was that this is super renormalizable and very good. And here we call it relevant, which means important in the IR. And as I'll show you later, this is actually considered a problem in Wilson's theory, these things. An example, we've talked about irrelevant operators in the Fermi interaction, but an example of a relevant interaction would be the Higgs mass. So here, we have an m squared Higgs squared in our Lagrangian. A scalar particle has dimension 1, and it's got a mass squared in front of it. Why is that bad? Well, if I take this Higgs boson and I couple to some new particle, then I get that the change in m squared is on the order of lambda squared, the cutoff, because this looks like integral d4p 1 over, say, p squared, if that's a fermion. So that looks like it blows up quadratically with the cutoff. And this is bad because even if you renormalize, the finite part should be, if this is a particle of mass m, then even if you get rid of the infinite part, the natural size for this would be big M. And so it's sort of like, if you find a light Higgs, it's sort of like, and you know that the theory has heavy degrees of freedom in it, like say you believe that there's a gut or something with mass, a grand unified theory with mass at 10 to the 15 Jev, then finding a light Higgs is sort of like walking into your lab and finding a pencil standing on its nose there. It looks like this is an incredibly exquisitely balanced thing. How in the world is that possible? So, an even worse example is the cosmological constant. That's the operator 1. It's just it's a number you add to the Lagrangian. And normally you'd say, well, I don't care about absolute energies, but gravity does, okay? And every loop of every particle contributes to the vacuum energy. And somehow the cosmological constant is less than 10 to the minus 3 electron volts to the fourth, or roughly 10 to the minus 3 electron volts to the fourth. How do you get a scale of energy density that low when you're coupling to so many heavy particles like we know of particles that go up to like 170 JeV for the top quark. So it's been turned on its head. These operators, which were problematic, are very simple. These, which were very simple, really are problematic in the new way of looking at things. And then the final one is if the operator has dimension d, this is called, I don't know what they used to call it, but here it's called marginal. Marginal means we don't really know if it gets more important or less important in the IR. Naively, it stays equally important. So an example would be the electron coupling to the photon. This electric charge is a number which doesn't have dimensions. And you look at the cross-section then for, say, E plus E minus goes to E plus E minus. And once you're at energies well above the electron mass, this goes like E squared over S, the only scale in the problem being the internal energy. And so your cross-section just scales with the energy. And this is sort of typical behavior of a theory with a dimensionless coupling. But when you look at quantum corrections, they actually change the dimension of the operator. And if you're in a perturbative theory, it might be something like alpha over 4 pi, for example. Well, what's its sign? So now I'm going to get an extra factor in my Lagrangian, which looks like S over lambda, my cutoff, to the plus or minus alpha over 4 pi, which I can write as e to the plus or minus alpha over 4 pi log S over lambda. So I get this extra factor multiplying my cross-section. Well, this becomes important when you have a very big, exponentially large, this is squared, sorry. When you have an exponential hierarchy between your cutoff and your energy. And I should have put in a plus or minus here. So it tells you that your theory becomes, gets a huge correction when you have an energy that's exponentially far away from your cutoff. And maybe this cutoff is, say, the Planck scale. We know we don't understand quantum gravity. We're not going to take our integrals above that. Well, if I had a minus here, then this would tell me that something weird happens at very low energy, such as, say, a GeV. And this is exactly what happens in QCD. The coupling of QCD gets a correction with a minus sign and tells you that something strong happens, some big corrections happen at an exponentially lower scale than the Planck scale, namely around a GeV. And this is really cool because it tells you can start from a weak theory at high energy and end up with a strong theory at a very, very low energy. That explains why you can have a proton that's so much bigger than the Planck scale. The proton's bound at the scale where QCD gets strong. The opposite example is QED, which has the plus sign, that says something crazy happens at an exponentially larger scale than the Planck mass. That's called the Landau pole. And for people like Dirac, that was a serious problem. Because what do you do with the theory if the coupling basically blows up? So what you find then is that the coupling constant does not look dimensionless. So if you have QCD, you find that it blows up at low energy. And here we have hadrons. This is where quarks bind up with each other in confinement. So that's sort of cool. And for QED, you have the opposite behavior. It blows up at something called the Landau pole, which is very, very high, much higher than the Planck scale. And so maybe you could say, okay, that's an artifact of our theory, we don't want to go that high. But there's something very strange that will happen with these theories when we look at it from Wilson's point of view. Wilson was driven by an interest of actually computing quantum field theory, putting it on a computer. So you can't be sort of wishy-washy about what you're doing with the infinities because computers don't do infinities, okay? So he chose for his cutoff to be a lattice. He made a lattice out of space-time so that there is a, you can't go below a minimum wavelength, so you can't go to high energy. And you have to define your theory at that lattice scale. So if you did QCD, suppose here's your lattice scale. On your computer, and you want to look at long-distance physics, you'll have a chance to see protons and pions and all these interesting things if you fix the coupling here to be pretty small, because it'll still get big in the low-energy worlds. But if you try to do that here, and to take your lattice spacing to infinity, what if I tried to take the lattice spacing here? Well, there's no way to do that if I want to keep down here, I want alpha equals 1 over 137 at the hydrogen scale. You can't have more than an infinite coupling at the cutoff. So you'd shift this thing over in order to do the computation. But the price you pay is now that alpha is much less than 1 over 137. And if I try to take this lattice cutoff to 0 to try to go back to the continuum world, I'd find that at the hydrogen scale, there's no interaction at all. It's called a trivial theory. So it is believed that theories that behave like this, which are called asymptotically free, make sense. You can take the limit as I go to the lattice spacing goes from 0, I just take the coupling smaller and smaller. I can do that on a computer. But with this one, if I want to go to short lattice spacing, even if I take the coupling huge at the lattice scale, I end up with 0 down at the hydrogen scale. This doesn't really worry us anymore because we know that electromagnetism is embedded in the standard model, which may be embedded in other theories, but we believe it could be embedded in an asymptotically free theory. I'll give another example of asymptotic freedom in a completely different context. Remember I said what's cool about this is that protons can be so much bigger than the Planck scale. There's a similar phenomenon in condensed matter systems, which is superconductivity. The Cooper pairs are maybe 1,000 lattice units apart in a crystal, in a metal. That's really weird. How do you get such big fluffy things wandering around in a noisy, dirty sample that don't get broken up by all the stuff happening between them? We'll see that it behaves the same way. So for the rest of today's lecture, what I want to do is let's channel Fermi and say we're going to pick the low-hanging fruit. We're just going to do dimensional analysis. We're going to write down some contact interactions for various things and see what they tell us. So the first example is going to be in the same line as what Fermi was thinking about, namely particle interactions. And what I'll tell you about is the program that Steve Weinberg sort of pioneered. He was very much influenced by Wilson's work, but unlike Wilson, he had no interest in doing computations on a computer. He wanted to do analytical calculations. And so what he pioneered was ways of using developing tools for doing effective field theory using Feynman diagrams. And in particular, he showed how useful dimensional regularization is for some technical reasons I won't go into. But he also was very interested in using, just doing a dimensional analysis and understanding what might lie beyond the standard model. So why was the Fermi interaction so interesting? Well, if you get rid of it, the neutron doesn't decay. So there's a symmetry somehow. There's a conservation law that is broken by this high dimension operator. There are no operators at lower dimension that'll give you neutron decay. So if you don't pay attention to the weak interactions, you'd say there's a conservation law for neutron number. And you say, oh, there's a symmetry. Every conservation law goes with a symmetry. But we know that symmetry doesn't exist. There's no symmetry that protects the neutron's life. So that's what we call an accidental symmetry. So you have a certain set of symmetries in your Lagrangian for marginal and relevant operators that forbid operators that break some other symmetry. An example in the standard model are lepton number or baryon number. Those are, you cannot write a dimension 4 or less operator with quarks or leptons that is consistent with SU3 cross SU2 cross U1 that also breaks lepton number or baryon number. So if they're broken, if the high energy theory breaks baryon number, it might break it incredibly strongly. It cannot appear in the standard model except for through irrelevant operators. So therefore, those conservation laws, baryon number and lepton number, will appear to be symmetries of our low energy world, but they're not symmetries of the short distance physics, they're accidental. So an example, which is sort of fun, is if you look at lattice QCD, you ask, what guarantees Lorentz invariance? As the lattice spacing goes to 0. That is definitely not a symmetry you've got in your lattice theory, right? Your lattice theory only has this sort of cubic symmetry, hypercubic symmetry. But we want Lorentz symmetry in the long run. How do I know I'm going to get Lorentz symmetry? Well, let's try to write down an operator that violates Lorentz invariance, but is symmetric under the hypercubic symmetry. Well, if I have a fermion I can write something like that, where del mu psi of x is psi of x plus a minus psi of x minus a over 2a. That's my lattice derivative. This is a hypercubic invariant. I'm summing over the 4 coordinates, space-time coordinates. But in the limit that a goes to 0, this turns into an ordinary derivative, and you get psi bar gamma mu d mu psi, which is Lorentz invariant. It turns out if you want to try to write down a term that breaks the Lorentz invariance, you can do it, but it's going to cost you. So for example, I could write down this one. So this violates the usual index summation convention. I got 4 of the same indices that I'm now summing up. This is hypercubic invariant. You can sort of see it because it looks like if I change mu from 0 to 1 and 1 to 2 and 2 to 3 and 3 to 0, this will be invariant because I'm summing over all the mu's. So this is hypercubic invariant. But in the continuum limit, okay, it would go like this, it would turn into this, which is not Lorentz invariant. But if you do the dimension counting, remember the fermions are 3 halves, so psi bar psi is dimension 3. And then I've got 3 derivatives, so it's dimension 3, 4, 5, 6. So its coefficient has to have dimensions 1 over mass squared, or length squared. And what the lattice does is if you actually just put this in and set a to 0, you find that you'll get an a squared out in front. Yeah.
Why did you jump from one derivative to 3?
I'm sorry?
Why did you jump from one derivative to 3?
I'm trying to write down an operator which is hypercubic invariant and is not Lorentz invariant.
Exactly, but wouldn't that happen also with just 2 derivatives?
So
you have 3 nu's, that would not be right.
right. With 2 derivatives, though, what's the problem? No, I think that would not be hypercubic invariant. It's the fact that there are 4 indices in a 4 space-time lattice. Yeah. So this has to have something in dimension length squared in front. So what appears when you take the small a limit is that this has an a squared out in front where a is the lattice spacing. So in the limit that a goes to 0, this goes to 0 as a goes to 0. And so you find that even though your lattice theory is not Lorentz invariant, your continuum theory is. Yes? Oh, sorry. Just waving. Okay.
So I'm a little bit confused. Are we adding 3, I guess, lattice derivatives, like the
Yes.
deltas? And then
Sorry, yeah,
saying-
this is...
Okay,
Yeah, these are...
okay.
Sorry.
And then we're taking that same limit.
And then you take the
saying
continuum
get-
limit, and what you find
get like
is
an accidental-
this thing, as a goes to 0. Yeah. And because of this term out in front, the thing goes away. So this is so Lorentz invariance is an accidental symmetry of lattice QCD. That's what makes it useful. If it wasn't, it wouldn't be very useful for describing the real world. So what Weinberg did, he's a very systematic guy. I remember as a grad student, I noticed that all the Harvard faculty were very liberal, with the exception of Weinberg. And I asked my advisor, Howard George, I said, is Weinberg going to vote for Reagan? And George, I said, well, his politics is like his physics. He has all the wrong instincts, but he's too smart to come up with the wrong answer. And it's true, you go to all these lectures and you see all these great physicists doing incredibly elegant things on the board. So Sidney Coleman was an example where you sit every day in quantum field theory was this work of art, and you'd come out and you'd say, wait a sec, I don't know how to do that. Weinberg would use the worst notation and would grind through these incredible algebraic calculations on the board and get to really cool answers at the end, but the process was so painful. Anyway, so he's very systematic. So he writes down all the operators of dimension 5, then he writes down all the operators of dimension 6, and so on. My very first experience with Weinberg was I'd come up with some idea, and George, I said, oh, you should go tell Weinberg you'd be interested. I said, really? So, okay, I was a second-year grad student, so I go knock on his door. And I made the mistake most grad students do, which is they think that the big professors know everything, and so you should just sort of telegraph your idea, not actually waste their time by explaining it in any detail. And within half a minute, he was saying, I don't have time for this shit. People come into my office all the time. I got to work. Get out of here. I went back to Georgia and said, was that really necessary? But later we had many good conversations when I became an adult. That was not uncommon to be yelled at Harvard. When I first arrived as a prospective student, I'd gotten into grad school and I was visiting to see if I liked it. And I was ushered into Shelley Glashaw's office, and the secretary said, we have a prospective student. He's sitting there writing. He says, go away, you won't get in. I said, well, I'm already in. He said, okay, then come, now go away. It didn't deter me. You get a thick skin there. I still went, yeah. Yeah, it does train you, though, to not burst into tears when somebody yells at you. Okay, so the standard model. The standard model means basically all the dimension 4 and less operators. So that's the gauge interactions, SU2 cross SU3 cross U1. It's got quarks, Higgs, leptons. let's look at dimension 5 operators. That's the lowest irrelevant operator you can write down. It turns out there's two types, and the one that's interesting is you take a lepton and a Higgs star. This has quantum numbers. These are both neutral under color. Under the weak interactions, this is half with a charge of minus a half, which I'll write this as a 2, sorry. So it means it's a doublet under SU2 and a charge minus a half under the U1. And the Higgs star is a doublet and charge 1/2. And you can make an SU2 singlet as long as you put an epsilon ij coupling to the SU2 numbers. So now you get an SU2 singlet. Okay, so that is dimension 3/2 plus 1, so that's dimension 4/2. Sorry, 3/2 plus 1 is 5/2. But you can't add this to the Lagrangian because this is a fermionic object. This is a fermion, that's a boson. So the spin is still a half. And you can't put that in Lagrange without breaking Lorentz invariance. But you can put this thing squared. And since that's dimension 5/2, the whole thing is now dimension 5. So it has a 1/lambda in it, where lambda is some new scale. This is the equivalent of G Fermi. For some unknown physics, so we have not seen this yet. At least Weinberg had not seen this yet when he wrote this down. What's interesting, though, is that this gives neutrino masses. So L looks like a neutrino electron, and H star. So when you give a VEV to H star, it's 0 V, where V is like 250 JeV. And when you contract with an epsilon, well, let's call this F, you get something that looks like nu F squared over lambda. So this looks like a neutrino mass. What's cool about it is that it's a neutrino mass from an irrelevant operator. So what does that tell me about the neutrino mass? Very small, typically. If lambda is big, this will be extremely small. So this is basically what's called the seesaw mechanism, which is that as lambda gets bigger, the scale of new physics, the neutrino mass gets lighter. And in fact, if you take lambda on the order of 10 to the 13 JeV or something like that, you get neutrino masses that are very much around the scale that we see. So this suggests when you now see neutrino masses, it suggests that it's possible, but not necessary, that you're looking at this operator. Why is it not necessary? Well, there could have been a right-handed neutrino in your theory, in which case it could couple to the lepton in a Higgs with a Yukawa coupling in a dimension 4 operator. If you did this, then given that the neutrino is around an EV and the Higgs VEV is 250 GeV, this would have to be a really, really small number to explain a light neutrino mass. So you have to fine-tune this coupling to be tiny in order to get a light neutrino mass. While here, it's automatic if lambda is just a big scale for new physics. So the prejudice is that this is what we've got, and not this. And there's another reason besides saying that Y has to be small. It's because I could just write nu R, you see, because the right-hand neutrino carries no quantum numbers under the SU3 cross SU2 cross U1. And so there's nothing to forbid me from putting in a big mass like the Planck scale. And so this seems unlikely, while this seems much more reasonable. And you can tell the difference because this has a lepton number symmetry where this has charge 1 and this has charge -1, or vice versa. Well, this one does not. There's no rotation I can do on the neutrino that leaves this invariant because they're the same object there. They're not conjugated. So this involves lepton number violation, this does not. This can be seen in neutrinoless double beta decay, which couldn't happen unless there's lepton number violation. So there are experiments to try to look for these things. How would this come about from short distance physics? Well, there are basically two ways you can draw a tree diagram that will give you that. I could have my lepton and my Higgs and a heavy particle, which I'll call N, and a Higgs and a lepton, like that. So that says that there is a U heavy fermion. In fact, if I had a Yukawa coupling to a right-handed neutrino with a heavy mass, then the low energy theory wouldn't have the right-handed neutrino in it because it's heavy, the effective theory. And the effect would come from this diagram. When I get rid of it, it would give me this operator. You say, well, wait a second, I thought you said that this preserves lepton number. It does, but this does not. So this would come from a high energy theory that does not preserve lepton number. You integrate out, you come up with the effective theory with no right-handed neutrino. This shrinks to a point, you get that operator. Well, another possibility would be there's some object that is exchanged between a lepton pair and a Higgs pair. Well, this is a scalar, that's a scalar, so this would have to be a scalar. And I believe it could either be a 1 or a 3 under SU2 weak. So there are two different types of models. There's the singlet Majorana and the triplet Majorana model. So we don't know. We think this operator exists. We're not even sure. We certainly don't know where it came from. But you can start looking at these different models and say, how would that affect cosmology? Is this helping with baryogenesis or other things? And so people play around with this. And this is an example of the short distance physics giving us hints about the long distance physics. Yes?
What's the suggestion for the scale of lambda?
I'm sorry, my hearing's terrible. Please speak up.
What's the suggestion for the scale of lambda?
What's the
Suggestion for the value of lambda?
The scale for
10
lambda.
TeV, 100 TeV.
Okay, so in both of these cases, sorry, with the background air conditioning, I really have a hard time. So in both cases, the mass of these guys would play the role of this.
And what is the
So numerically, we don't know, okay? But we know from neutrino masses that we know there aren't any neutrino masses at, say, 10 MeV. So we know this has got to be bigger than something, okay? And if you want to get this to give you the right, since we know the VEV of the Higgs, and we know that the neutrino mass splittings are on the order of 10 to the minus 2 eV, something like that, then we can get an estimate for lambda that it's somewhere, and it'll depend on the coupling constants too. It could be higher scale and smaller couplings, but probably above 10 to the 13 JeV or something. Interestingly close to the same scale you see in grand unified theories, which I'm going to come to next. This is a couple other dimension 5 operators you could write down, which are Q bar, sigma mu nu, F mu nu, Q, and Q bar, sigma mu nu, F dual mu nu, Q, where Q are quarks. Well, actually, they could be also leptons. And this contributes to a magnetic dipole moment. And this is the electric one. Now, we know that at very low energy, we know the neutron has a magnetic moment, but it's chargeless. So the usual way of getting a magnetic moment from a coupling like that doesn't exist for the neutron. So the neutron magnetic moment would have to come from an operator like that, if you're looking at a low energy theory. And you can explain this by saying, well, there's some, say that there was a charged particle here. So the neutron turns into a proton and a pi minus, and then back into a neutron. And then the photon could couple here, or the photon couple there, because those are charged particles. And that could be the origin of the neutron magnetic moment. When I think it was Rabi discovered that the magnetic moment of the proton G wasn't equal to 2, which is what the Dirac theory predicted. It was the first evidence that the proton is not a point particle that could be described with the Dirac equation. Yeah.
So are you saying that the operator with down quarks contributes to the neutron movement? Or there's an effective field theory with an operator like that, where the neutron is...
If I'm at low energy, I can write down an effective operator like this. And if I'm at extremely low energy, say below the pion mass, this is sort of a picture of what short distance physics could have given rise to it. But this is not that interesting, because magnetic, especially for charged particles, because they already get a magnetic moment from this operator here. This, however, violates CP. And in particular, it gives an electric dipole moment to the neutron. And so there are extensive experiments, many experiments looking for a neutron electric dipole moment, because we've seen CP violation in the standard model through, say, kaon decays. And we know we need CP violation if we want to explain the origin of matter in the universe, baryogenesis, coming from scratch, because baryons violate CP if you start it off because if you do a charge conjugation transformation on our universe, it turns into antimatter and doesn't look the same at all. But if it starts from equal matter and antimatter, then somehow charge conjugation must have been broken, and it turns out parity too. So it's interesting to look for new sources of CP violation, but so far they haven't found it. They put bounds on this. So this is a tricky operator. It looks like it should have a 1 over lambda in front of it because it's dimension 5. But it violates chirality. It mixes left and right. So in most diagrams you could write down, you get a factor of the mass of the quark upstairs, and you get a lambda squared downstairs. So usually this behaves like a dimension 6 operator, because the only way that chirality can be violated in your marginal and relevant operators is through the quark mass. And so if you look at a diagram that connects a left to a right-handed quark, it typically will have a power of the quark mass in it. So this behaves like dimension 6. Other dimension 6 operators, though, are fascinating. Baryon number violation. Conventionally, we think of the proton as a stable particle, but it might be radioactive. It might want to decay. For example, if baryon number wasn't conserved, it might be able to go to a pi 0 and a positron. That conserves charge. It's got a fermion on both sides. That would be a disaster for us if it happened at any speed at all. Well, I can write down an operator that violates baryon number, but it's going to have, the quarks are colored. And in order to carry baryon number, I have to have quarks and not quark and antiquark. So I have to have at least 3 of them to make a color neutral object. So this is A, B, and C with an epsilon to make it color neutral. And now that's a fermionic operator because it's got 3 fermions, so I need another fermion in there. So I could put a lepton there. And it turns out you can make operators like this. There are quite a few, especially when you include multiple different types of flavors. Many operators like this. This is 4 fermions, so it's dimension 6, and so it's going to have a 1 over lambda squared in front of it. And it can be used to do something like that because I can write QQQ. That operator, when I go down to an effective theory of the strong interactions, I can think of that as with some amplitude Z1 producing a proton, plus some amplitude Z2 producing, say, a neutron and a pi plus, or a proton and a pi zero, and so on. So dimensional analysis, what is the proton lifetime? Well, let's look at the proton width. You get this from a squaring a Feynman diagram. So it's going to have to go like 1 over lambda to the 4th. This is the inverse lifetime. So its dimension is mass, because the lifetime is the time, which has dimension inverse mass. You have an inverse lifetime. So it's got to have some mass to the 5th out in front. Suppose you're looking at and it must come from phase space. So here's the diagram. It looks like a Fermi interaction. I'm squaring it to get that. Well, again, phase space. So let's imagine the pi zero is, well, it is much lighter than the proton. So the only scale around really is the proton mass. That's how much energy is going into the outgoing particles. And so you expect something that goes like m proton to the 5th on the front. And we have phase space integrals and so on. You also get 1 over 4 pi's and so on. I won't try to estimate those. But, well, actually, for two-body final states, you typically get a 1 over 8 pi. Counting pi's is more of a art than a science, unless you do the calculation. So, when grand unified theories were first discovered by Georgia and Glashow, they worked out the group theory together. It was really cool. You could put all of SU3 cross SU2 cross U1 in a single group, SU5. So there's only one coupling constant. So you can relate the electric coupling constant to the weak, to the strong. Seemed really cool. Georgia goes home after dinner, sits down to work out some details of the theory and discovers, oh no, it violates baryon number, because there were graphs where you could have a Q and a Q, and then they had colored gauge bosons, which I'll call X, which could turn into a Q and an L. Yeah.
These kind of operators so the base assumption is that some unique completion to some higher energy theory that is renormalizable. That basis assumption so that.
Can you repeat it again?
It's the base assumption that the theory for any of these operators is renormalizable at some higher energy scale, and this is some UV completion of this.
Sorry? If these things renormalize at some higher scale, and you can just use the completion of these operators.
So that even if it's not renormalizable at low energy, it is renormalizable. It is some approximation of what
Yes, so in the grand unified theory, where this is due to an X boson, this is now an asymptotically free renormalizable theory. Just like the Fermi interaction is not renormalizable, but it doesn't matter because you're going to take it up to a scale lambda. And then you can start going to the theory with the gauge bosons, and then it becomes renormalizable. Though, don't get too happy because we still have quantum gravity. We don't know how to renormalize that, okay? So there's still a lot of mystery what's happening up there. Anyway, Georgia came home and then he saw this diagram and he said, oh no, the proton decays. And he felt miserable because it's such a beautiful theory and now he'd have to throw it out. So he had a glass of scotch and that loosened up his inhibitions. And he said, let's make it really heavy. Now you have to understand that, so when I was a grad student, I remember seeing papers that said, maybe there's a top quark and maybe it could be 10 GeV, which is why we haven't seen it. And that was considered ridiculously high energy. That was so daring to say that there's a particle at 10 GeV. But what's the mass of the X to make this viable? Well, for a lifetime of, a proton lifetime bigger than 10 to the 34 years, which is, I think, current experimental bounds, at least for some decay widths are up to 10 to the 35 or so. if you say that this is the experimental requirement and you use something like that, you find that lambda has to be bigger than or on the order of 10 to the 15 GeV. A ridiculously high scale, sort of tantalizingly close to the Planck scale, which is 10 to the 19. But, so he said, okay, we'll just make it super, super heavy, okay? And then we'll tell the experimentalists to go look for it, to look for proton decay. Yeah, I want to return to one thing that was sparked a bit by your question, I think, about how the effective theory turns into the high energy theory. So let me just go back to loops in the Fermi theory. And let's look at this correction again here, which this goes like G Fermi squared, and then it's a loop, so typically a 16 pi squared. And then we said there had to be a lambda squared. Sorry, you can't see the answer. Sorry about that because of the pillar. Okay, well, let's remember G Fermi, we know from the standard model is really something like G squared over MW squared or MZ squared. And I tell you that lambda has to be on the order of MW. I can't take my cutoff higher than MW because I'm not putting the W in my theory. Remember, the rule was you have to include all the particles lighter than lambda in your theory, and I'm not putting the W in. So this is the highest lambda could be. If I look at the correction then, this goes like G to the fourth. Well, let me pull out one factor G Fermi, which is the tree level result, and then it's times G squared over MW squared from the other G Fermi, and then an MW squared over, say, 16 pi squared from the loop. The MW's cancel, and you see that this is something that goes like G squared over 16 pi squared, G Fermi. And so in fact, this is a correction which is big or small compared to the tree level one, depending on whether the high energy theory is perturbative or not. And so it moves smoothly into the perturbation expansion of the high energy theory if the high energy theory is weakly coupled. So you sort of have two expansions going on at the same time in your effective theory. You've got the momentum expansion, but you also have the underlying perturbative expansion of the short distance physics. Okay, I'm out of time, so I'll continue next. No, you can. I'll answer a question, but I won't continue with my lecture.
So then we were just talking about this. Does that imply that if we had some type of strong coupling with whatever interaction we're trying to model, that we would lose any semblance of, say, renormalizability?
We'd lose part of the expansion. We'd lose the perturbative expansion. We'd still have the fact that higher derivatives give you smaller and smaller answers at low energy. But when the theory goes to higher energy, everything would break down. Because now all the higher dimensional operators are just suppressed by powers of G squared over 16 pi squared, which you told me is order 1. And an example of such a theory is chiral perturbation theory, where we look at the effective theory of mesons below the scale of QCD, where when you get to the cutoff, it's a strongly coupled theory. So we still have the derivative expansion, but it really breaks down when we go up to high energy.
I guess, was it still like useful or effective in predicting some level of phenomenology, even though it breaks down when we get the whole expansion seems to break down?
Right. Well, the expansion breaks down in a funny way. It's that it looks like operators renormalize each other, and therefore in a way that you can't control. But it turns out this is where dimensional regularization comes in. That dimensional regularization ensures that operators only renormalize higher dimension operators. So if I say I'm only interested in the first 4 operators in my expansion and not interested in the higher dimension operators, I don't have to worry about those things. I'm excluding renormalizing the ones I'm studying. So that's a technical thing, but that was a contribution from Weinberg that was useful. Other questions? Yeah.
So I have a question about the lambda pole of QED. So you said that its existence would imply that the coupling, that in the IR is essentially zero. But strictly speaking, I would assume that there must be some, well, mathematical problems. It just means that the extrapolation from the UV to IR is not stable, and you can get whatever you like. Or it's not true.
No, I don't think so, because the thing is, it's not just that it gets bigger and bigger in the UV. It becomes infinite at a finite scale in the UV. And so if you just try to imagine, like Wilson, how would I put that on a computer? Okay, and I want to take the lattice spacing smaller than the Landau scale. I can't put in a coupling that's bigger than infinity. If I put even infinity at a scale that's much higher than the Landau scale, I get 0 at long distance. Or another way of saying it is that if you wanted to look at the interaction between charges, say static charges in QED at arbitrary long distance, you'll find that there's no interaction at all. It doesn't fall off like 1 over r, it falls off faster than 1 over r at long distance. And we understand that perfectly well due to screening. The E plus E minus pairs in the vacuum screen this charge, so that actually when you're far apart, you don't see the same charge. So that's what's going on, it's just screening. But screening means that you can't take away the cutoff and have a theory that has interactions, because our scale, whatever scale we're doing the experiment, it looks infinitely long compared to the cutoff. And so you always have an infinite amount of screening, or total screening of your charges. What's weird about QCD is that there's anti-screening. The gluons make the color charge look bigger and bigger at longer distances.
Any more questions for David?
I have another. So going back to when you were talking about the old school, I guess, thought versus Wilson's kind of understanding. When we're talking about non-renormalizable theories, Wilson is essentially saying this is irrelevant because the IR corrections are.
So at low energy, they're very small. And through this argument here, if your underlying theory is perturbative, then it'll still be perturbative all the way up to the cutoff. And you don't have to talk about physics above the cutoff. And if he wants to do QCD, he's willing to get rid of this. He's able to say, I'll set the coupling on the order of g squared over 4 pi squared on the order of 1 if you wanted to have a low cutoff. But the cool thing about QCD is I can go to a higher cutoff and g squared over 4 pi gets smaller and smaller because of asymptotic freedom.
So he's literally saying that as far as like this effective field theory approach goes, there's not really like a relevance whether or not like the theory we're trying to model is,
Right.
I guess, classically renormalized.
Right.
Okay.
As long as if you really want to be able to talk about overall scales, it would have to be asymptotically free. But we don't worry about that because we think QED is probably embedded in a grand unified theory that is asymptotically free because it's a non-abelian gauge theory. So that happens well below the Landau pole. And this is just an example, which is, don't get your panties into twists over stuff you don't see experimentally.
Okay. Yeah.
Mark?
Since you mentioned the Landau pole now, at what energy is that expected? Because I assume when you look at the coupling constants and you talk about the grand unified theory, you want to bring this together and your theory.
It is so much higher that you don't have to even think about it. It's the Landau pole. Is something like m electron times e to the 4 pi over alpha. 4 pi over alpha is 1,000. So you're talking about 10 to the 1,000, e to the 1,000 times the electron mass. So it's way above the Planck scale, which is 10 to the 19 Jeff.
So it doesn't have any real realization. Because
but there's another theory.
QCD coupling constant, right, where it basically blows up. That's the regime of nuclei hadrons, what you talked about. But the Landau pole doesn't have anything where you'd say.
There is an
this is what
example.
happens.
There is an example of a theory that could have been where it would have been important, which is that in the standard model, the 5/4 coupling of the Higgs behaves like this. If the 5/4 coupling was large at the W scale, which means the Higgs was heavy, it would get strong very quickly. It would be strong at a TeV. So it was known that if the Higgs turned out to be heavy, there would have to be new physics coming in relatively close to the W mass. You wouldn't have to go up very far. As it is, the Higgs is light enough so that you don't run into problems until you get up to the gut scale. But again, the gut scale up here is a place where you better fix the Higgs mass.